In this recording, we're looking at sections 4.1 and 4.2, which describe certain types of chemical reactions that occur, mainly in aqueous solution, and the nature of aqueous solutions themselves. And so we'll start by talking about the three different types of chemical reactions: combination reactions and decomposition reactions, which are opposites of each other. They're opposite types of processes. And we'll finally look at two different kinds of displacement reactions. Then we'll explore the nature of aqueous solutions. We'll first talk about what does it mean for something to be dissolved in water, which is what an aqueous solution does, what happens when something dissolves in water. Then we'll categorize different types of electrolytes, as well as define the rules by which we can predict whether particular ionic compounds are soluble or not. Let's start with types of chemical reactions. Combination reactions are what they sound like. It's when two things combine to form one thing, or two or more things combine to form one thing. And so most reactions between two different elements to form a compound are combination reactions. So the reaction between hydrogen and oxygen to form water is a combination reaction. Another reaction is that between a compound and an element to form what will need to be a larger compound. This one's between sulfur dioxide. It reacts with oxygen to form sulfur trioxide. The fact that there's two of one reactant and one of the other reactant doesn't matter. It's two different things forming one thing and one kind of thing. And this is a reaction that, not so much now, it used to be a big concern for acid rain, because sulfur dioxide was made when dirty coal was burned in power plants. Most of that's scrubbed out now, but when dirty coal contained sulfur, it made sulfur dioxide in a power plant that reacted with oxygen to make SO3. And in a second combination reaction, SO3 reacted with water to make sulfuric acid, which then came down in rain. A lot of other combination reactions are those between elements and other elements to form compounds. So, for example, the reaction of two mercury atoms with an O2 molecule to make two mercury 2 oxides, that's a combination reaction. And so most reactions between two different elements will end up being combination reactions. The opposite of a combination reaction is a decomposition reaction, where one thing falls apart to form two or more things. And so the opposite of the formation of water is a decomposition reaction. This actually doesn't happen spontaneously. It needs energy. So you have to add energy to do that. And pretty much the only way that really gets done in practice is with electrical energy. You can electrolyze water to form hydrogen and oxygen, and that's a decomposition. Another kind of decomposition reaction that's very common is heating up what are called metal carbonates. So here's a metallic atom. It's an ionic compound with a carbonate. If you heat it, a delta sign in chemistry over a reaction arrow means heating it. If you heat it, you essentially remove carbon dioxide. So that's decomposing to form calcium oxide and carbon dioxide. So a decomposition reaction, one thing breaks up into two or more things. We're going to look at single displacement reactions, which are far more, single and double displacement reactions, which are far more common than are either combination or decomposition reactions. In a single displacement reactions, one part of a compound is replaced by another. So you have a compound A bonded to B. And what happens is X comes in and knocks A out. So X takes the place of A. X is displacing A, and so A is now no longer part of the compound, and X is. Most of these reactions involve metals, and so one example would be copper 2 chloride reacts with magnesium, and the magnesium displaces the copper to form magnesium chloride, and copper, which is now displaced. A similar reaction, which is a little harder to see, is the reaction of water with sodium. And so water with sodium react to make hydrogen and sodium hydroxide. It's a little hard to see what's happening, but if you draw out the water molecules like that, what's happening is the sodium's coming in and it's displacing one of the hydrogens to make sodium hydroxide, and those hydrogens in and of themselves are not stable, so they form H2 gas molecules. A double displacement reaction is by far the most important of all these reactions we're talking about, and that's where two atoms or ions exchange. So if you have A, B, and X and Y, B ends up with X, and Y ends up with A. And most of the time, these involve two ions exchanging. And so the first, we're going to look at three different kinds of these reactions. The first is a precipitation reaction, where you have two soluble ionic compounds. You know they're soluble because of the aqueous symbol, which means dissolved in water. And what happens here is the lead ion, lead 2+, ends up with the sulfate ion. Potassium ions end up with the nitrate ions. And so you end up with potassium nitrate and lead sulfate. So the two ions have swapped. In this particular case, in this particular example, the lead sulfate that you make happens to be insoluble, so it precipitates. And we often write a PPT as a precipitation. The other thing you'll see very often in reactions is a little down arrow, which means it precipitates, and that solid sinks to the bottom of the beaker or flask you're doing this reaction in. So precipitation reactions are double displacement reactions where one of the products happens to be insoluble. An acid-base reaction is also called a neutralization reaction because the acid and base neutralize each other. They neutralize their acid or base effect. And in this case, what happens is the hydrogen from the acid ends up with the hydroxide from the base. And the sodium ion, the cation, ends up from the base, ends up with the anion from the acid. And so when the H and the OH combine, they make water. When the H and the Na plus and Cl combine, they make NaCl. And very often you say that when a strong acid, which HCl is, and a strong base react, you make water and a salt. You don't always make NaCl as the salt, but you make a salt. So if you did, say, HBr, which is another strong acid, plus, say, potassium hydroxide, you would make water. It's a different salt. You would make HBr. Gas-forming reactions are the last form of double displacement reaction, and in reality, they're just another kind of reaction, often an acid-base reaction that has a secondary reaction. So if nickel carbonate reacts with HCl, it undergoes double displacement reaction where the H's, the H plus ions, end up with the carbonate ion to make H2CO3, which is carbonic acid, and the nickel ion ends up with the chloride ion to make nickel 2 chloride, nickel chloride. What makes this a gas-forming reaction is that the carbonic acid that gets made is unstable and breaks up into water and carbon dioxide, and carbon dioxide is gas. And you don't so that it leaves, it degasses out of the solution. So if you actually add these two reactions together, the overall reaction is that the nickel carbonate reacts with HCl to make nickel chloride plus water and the carbon dioxide. This bottom overall reaction would not necessarily be easy to recognize as a double displacement reaction, but realize the first reaction that actually happens is this first one, which is clearly a double displacement reaction where two things here are swapping places with the two things there. Okay, now let's turn to aqueous solutions. Aqueous solutions, by definition, mean things dissolved in water. And the things that are dissolving are called solutes, and the water is the solvent. These are categorized, different things dissolved in water are categorized by how well they dissolve, and also what happens to the nature of the solute when it dissolves. And by that we mean, does it break up into ions or not? And so let's first talk about what happens when something dissolves. When, say, a sodium chloride dissolves, when salt dissolves in water, NaCl, what happens is each of the components that's dissolving, this here is our NaCl, solvent. When it dissolves, it's surrounded by water molecules, and that's called hydrated. So there's a hydrated chloride ion. This is a hydrated sodium ion. And the same thing will happen even if there aren't any ions. If you have, say, an alcohol like CH3, which we'll look at in a little bit, OH, when it dissolves in water, there'll be water molecules all surrounding it as well. And so when water is the solvent and things dissolve in it, when they dissolve, you'll have this solute, either molecule or ion, surrounded by water molecules, and that surrounding process is called hydration. And that's an important part of why things dissolve, because they become stabilized when they become hydrated. So let's do our categorization of electrolyte. A strong electrolyte is one in which when the compound dissolves, it fully forms ions in solution, 100%. And so when sodium chloride dissolves, all of the sodium chloride makes up the sodium ions and chloride ions. So if you had 1 mole of sodium chloride, you'd make 1 mole of sodium ions in solution, 1 mole of chloride ions in solution. And it's important to realize that the sodium and the chloride, after they dissolve, really don't have any contact with each other. Going back to this picture, the chloride ion is here, surrounded by water. The fact that they came from sodium chloride is no longer important. You just have chloride ions in solution, and you have sodium ions in solution. Weak electrolytes are similar, but in fact they don't break up. They form ions in solution, but not completely. And so this is acetic acid. It's a weak acid, and it's weak because it does not ionize 100% in solution. So what happens is it breaks up into acetate ions. But the idea is, by not meaning 100%, we don't mean that the molecule, a molecule, splits up a little bit. We mean if you have a lot of molecules, only a few of them break up. Let's go back and look at the sodium chloride example for a second and show the difference here. Sodium chloride, if it breaks up in solution, what happens is, once it's dissolved, if there's water all around here, the sodiums and the chlorides all go their separate way. And the idea is all around here not shown are water molecules. So the sodiums and the chlorides were together, and now they're all apart. For a weak acid, which is a weak electrolyte, let's look at a different example, HF. HF is a different weak acid. It breaks up into H plus and F minus, but less than 100%. What happens is, when it dissolves, it starts out with all of the HFs connected as HF molecules. When they're dissolved, most of them stay as HF molecules, but just a few of them break up. So you have a lot of HF molecules, and maybe 1, 2, 5, 10% break up into H plus and F minus ions, but most of them remain as HF molecules. So that's a weak electrolyte because most of them don't break up. A non-electrolyte is a solute molecule that just doesn't form ions. And so let's look at an animation of that. This is methanol. When methanol dissolves in solution, it doesn't do anything. It floats around and it's hydrated, but it doesn't break up into any ions, so it doesn't form any ions. Water itself is a non-electrolyte because it doesn't break up into ions, or there's not very many itself. And so when something like the methanol molecule is in it, there aren't any ions, so it's a non-electrolyte. In general, strong electrolytes are a solution that conducts electricity well. And the compounds that are strong electrolytes are soluble ionic compounds and strong acids. Those are the two categories of compounds that always make strong electrolytes. Weak electrolytes will, when dissolved in water, conduct electricity poorly. And the compounds that are generally weak electrolytes are normally weak acids and base ammonia. And non-electrolytes don't conduct electricity when dissolved in water. And most molecular covalent compounds are non-electrolytes, other than the ones that are strong acids or weak acids. Those are the ones that are the exception to that general trend. So when we talk about solubility, what we're talking about is whether or not something actually dissolves, an ionic compound dissolves in water. And the general idea is you've got this salt, MX, and this is some cation that can be like, say, Na plus, and X anion can be like a nitrate ion, any ion. And the question, when you ask, is something soluble or not, is does it break up into ions when it dissolves? Does it form ions when it goes in solution? Or does the MX solid just stay together and sink to the bottom of the beaker? So does that happen? If it does happen, the compound is soluble. If it does not happen, the compound is insoluble. That's the idea of the definition. But it's a little more complicated because sometimes it dissolves just a little bit and not a lot. And so what's the cutoff? And different people have different cutoffs. There's no official cutoff for whether something is soluble or not. But we're going to use 1 gram of solute dissolving in 100 grams of water. If more than a gram dissolves, it's considered soluble. If less than a gram dissolves, it's considered insoluble. But things around there are called moderately soluble or sparingly soluble. You can predict the solubility of most ionic compounds, not all, but most, using a set of guidelines or solubility rules. And it's split up into 2 different parts. Rules for things that are generally soluble and rules for things that are generally insoluble, that is not soluble. And so let's look at the ones that are generally soluble first. All compounds that have the cations sodium and potassium or ammonium, they're generally always soluble. There might be a few special cases when that's not the case, but generally those are all soluble. So those are the cation rules, the cations that are always soluble. There are also certain anions that are always soluble, no matter what cations they're with, and those can include nitrate, acetate, chlorate, and perchlorate salts. So those are things that are always soluble, things that contain either those cations or those anions. Most chlorides and bromides and iodide salts are soluble with these exceptions. Those salts that contain lead 2+, silver+, or mercury 2+. Those are the exceptions rule, so those are insoluble. Most fluoride salts are soluble with these exceptions: calcium, strontium, barium, and lead. Most sulfate salts are soluble, except for these ones here: lead, barium, strontium, mercury 2+, and calcium. Other ones are soluble. So what you would say is, if I told you had, let's say, potassium fluoride, is that soluble or not? The rule is that all potassium salts are soluble, so yes, that is soluble. The other rule is fluoride salts are generally soluble. These are the exceptions. Fluoride and potassium together are not an exception, so again, it's soluble. If you had barium fluoride, there's no rule for barium up here, but there's a rule for fluoride. Fluoride salts are generally soluble, but barium is an exception to the rule, so that's insoluble, because it's an exception to the solubility rule for fluoride. Now let's look at the other side of the coin, so to speak, and look at things that are generally insoluble. Most hydroxide compounds are insoluble. Most oxide compounds are insoluble, with the exceptions that we've already talked about, that sodium and potassium salts are generally soluble. In this case, also barium hydroxide is soluble. Most sulfide salts are insoluble, with the exceptions we've talked about before. And most carbonates and phosphate salts are soluble, with the exceptions we've talked about before. So if I said you had calcium phosphate, which would be Ca3PO4, is that soluble or not? The rule is that most carbonates are insoluble. Calcium is not an exception to that rule, so that's insoluble. Okay, so let's use the full chart and just ask a couple of questions. Let's say lead carbonate. Is lead carbonate soluble or not? There's nothing up here about lead in terms of lead salts being always soluble. There's nothing in here about lead salts being soluble or not. But there is a general rule that carbonate salts are generally insoluble. Lead is not an exception to that, so lead carbonate is insoluble. Let's talk about potassium hydroxide. We have a rule that hydroxides are generally insoluble, but potassium is an exception to that rule, so it's soluble. It's also soluble by the rule that all potassium salts are soluble. Let's think about barium sulfate. The rule is that sulfates are generally soluble. Barium is not one of the things, it is one of the things that's an exception to that rule, so that's insoluble. Page. We've got iron 2 sulfate, FeSO4. Nothing on this chart at all about iron. Sulfates tend to be soluble. Iron is not an exception to that rule, so iron 2 sulfate will be soluble. Iron 3 sulfate, which would be Fe2SO43, that's also soluble, because it is not an exception to the rule that soluble sulfate salts are soluble. And that's generally the way you do it. You look for things that have rules, and then you see if the thing you're talking about is an exception to that rule. And so you can now tell the solubility, predict the solubility of hundreds and hundreds of compounds.